All right. So what we're going to go over is just kind of finish up, and I'm going to recover a couple of things here to do with global wind patterns. Okay. The big thing about global wind patterns is it's a focus on the most important method of heat transfer that there is on Earth. Okay. The one that is responsible for weather. Okay. For movement of almost all energy to do with climate and things like that on Earth, and that is convection. Okay. We talked about that near the end of lesson 3. Okay, we were talking about the environmental triad, and we were looking at conduction, convection, and radiation. Convection is the movement of a fluid due to changes in energy or differences in energy. Well, the fluid we're talking about here is air, and the movement of air is wind. Okay, that's basically what this lesson is all about. Okay, convection is the movement of a fluid. The fluid we're talking about is the atmosphere, the air in the atmosphere, and that's going to be wind. When that starts to move, that's how we perceive that movement of air. All right. Now, when that air moves, not only is it going to carry and move sensible heat, that is bringing warm air, okay, to another area, or bringing cold air to another area, okay, but it's also going to move latent heat. And latent heat is just as important, if not more important, than sensible heat. Okay? Latent heat, if you recall, is the heat that is carried by water vapor. Okay? It takes energy to evaporate water. Once that water becomes a vapor, becomes a gas, and it starts to move along with the air in the atmosphere, the energy that it has gained because it has changed from a liquid to a gas is carried with it. When that vapor and that gas get to a new area and turn back into a liquid, which they eventually always do, that energy is released into that new area. Okay? And we will detect that as sensible heat once it turns from latent heat back into regular sensible heat. All right? So it is a way to transfer huge amounts of not only moisture, but also energy from a place getting more energy than another. In example, the equator to the poles. All right, everybody with me there? All right, we're going to look at the mechanisms of that here in a minute. Okay, before we talk about the mechanisms involved in mostly this, we also need to look at the jet stream. Okay, the jet stream is a high altitude wind, okay, that changes location all the time. It changes location because of the location of areas of high and low pressure. Most of the time it's pretty consistently around the same place, but occasionally you get a massive air system move in that's either really high or really low in pressure. Mostly high pressure moves things around, and it alters the path of the jet stream, because the jet stream can't just go through a high pressure area. Okay? It gets deflected because rotation around these kind of high and low pressure areas results in rotation. Okay? So the jet stream gets deflected, and when it does that, it's carrying latent heat. Okay, from more equatorial areas. And it's bringing that in. When it does, and it gets deflected up and into colder areas, it's going to transfer a lot of that latent heat, drop it off. Okay, in the form of, hey, here's some water vapor. Okay, oh, it's really cold here. This water vapor is condensing and falling as precipitation. And that's what we see right here. Okay, typically in this area of Canada, there is a high pressure area, typically. Okay, and so the jet stream is either moving below it, but very rarely above it. All right? Just how big is this high pressure area determines how far does the jet stream get knocked out of its regular path. How far down does it get pushed, or out of the way does it get pushed? Okay? I chose this map here because it's an extreme situation that almost never happens, but it resulted in extraordinarily stormy, unstable weather for several days. Okay, because of these things. So we had all this warm, moist air coming through the jet stream, coming with the jet stream, and it encountered this chilly, high-pressure air that forced it downwards. When they encountered each other, all of the water vapor that was in that air mass was forced downwards and cooled rapidly, which resulted in high levels of thunderstorm activity, levels of precipitation, and all that kind of stuff, because you have these two types of air masses that are very different. Okay, when they interact, sparks happen. Okay, that's lightning, right? And we get all of this kind of unstable weather. So all through here, okay, was very unsettled. Thunderstorms tracked through there for days on end. Okay, tornadoes, all that kind of stuff. Okay, because of the interaction of these places, forcing the jet stream being forced to go to places it doesn't normally go. Right? Watching the jet stream is a meteorologist's best indicator of being able to predict the next few days. Okay? If they see a jet stream moving in a certain way, they know that on one side of that, there's going to be this kind of weather, and on the other side, there's going to be this kind of weather, at least for, you know, the foreseeable future, a few days, right? We all know that, you know, being a weatherman is the only occupation you can have where you can be wrong all the time and not get fired. Okay, because you know that happens. You're predicting the weather. You're not telling us what it's going to be. You're taking your best guess using the data you have. Does the stuff always work out exactly the way they think? Not at all. All right. There's lots of times where I open up the weather network app on my phone and it says Okotoks, sunny and 19, and I look out the window and it's pouring rain. Okay, yeah, it's not always going to be 100% accurate. All right. That's when you go to the weather rock. Was that on the? Did I talk about the weather rock in the podcast? Okay, you can have the weather rock. Take a rock, any rock, tie a string around it, and hang it in front of the window. If the rock is moving, it's windy. If the rock is wet, it's raining. If the rock is white, it's snowing. It's right 100% of the time. Okay? The weather rock is never wrong. It's never going to tell you what it's going to be tomorrow, but it'll always give you the current conditions accurately. Keep that in mind. Okay, there's actually a place online where you can buy weather rocks, and yeah, it's silly, but yeah. All right, so does everyone understand the role of the jet stream? The big thing with the jet stream, guys, big thing with the jet stream is its role with latent heat. Okay, it moves that moisture around. Okay, that's its big role. Not saying that convection can't move water vapor and moisture as well. It can, but the jet stream has these weird patterns where it moves north and south in this kind of serpentine pattern. And it does that a lot. Okay? And so it's more consistently bringing in strange air masses that can cause rapid changes in weather. Okay? If you are a person who is like at high altitudes often, let's say you're making a summit attempt on like Everest or K2 or something like that, you are always closely monitoring the jet stream because at the altitude you're at, you could actually be in it. Okay? And the jet stream moves at an incredibly high rate of speed, and if it crosses the mountain while you're on it, the weather's going to change rapidly for the worse usually. Okay, so what you do is you watch not only the weather radar and all that kind of stuff, but you watch the mountains that are a few kilometers away. And if you start to see what they call spin drift, which is curling wisps of snow being blown off the tops of mountains that are nearby, if that pattern is moving towards you, you leave. Okay? You do not continue your summit attempt. You go down the mountain, and you go down the mountain as fast as you can, because if you don't, you're going to get trapped up there. Okay? When that jet stream crosses and brings in that other air that has all the moisture, at that altitude, it's going to be a complete whiteout blizzard conditions, and that's when people get caught on the summit and die. Okay? I was reading this article the other day talking about all the bodies that are still on Everest, because they don't bring them back, right? Like you would die bringing back a person who had died because it's so strenuous and so hard, right? So there's bodies that people actually use as markers on the way up. Okay, and there's a place also called the Rainbow Valley. And it's called the Rainbow Valley because that's where many of the bodies fall, and you can see their coats, all of their jackets and stuff. Yeah, different colors down at the bottom. It's quite morbid, actually. Okay. Well, the problem is that it's very cold up there, right? It does, so they don't decompose. They're just kind of mummified, okay, by being frozen. Yeah, it's quite disconcerting. If you've ever watched any documentaries on Everest, there's almost always a scene where they walk past. You know, all the bodies have names. They know who most of them are. Okay? Yeah, and there's just nothing they can do. You can't fly a helicopter to that level because the air is too thin for it to work. So there's no way to retrieve those people, unfortunately, because there's no oxygen and it's impossible to do. These people that climb Everest, they can run back-to-back marathons at sea level. When they're climbing the top of Mount Everest, they take one step, stop, and breathe heavily for like 30 seconds before they can actually take one more step, if they're climbing without oxygen. If they're climbing with oxygen, they take 2 or 3 and stop. It's savage, right? There's just no air up there, okay? It's horrid. Okay, everybody follow the role of the jet stream. Something I might ask about on a test would be explain how energy could be transported from equatorial areas to polar areas. You would need to identify some of the mechanisms. One of those mechanisms is the jet stream. Convection winds would be another. Okay, explain how those work. All right, prevailing winds. Here in Okotoks, our prevailing winds are typically from the southwest. Okay, that's not only because of the way the mountains are set up, but it's also because of our latitude. Okay, where we are on Earth determines which way the winds typically come from. Right? Near the equator, the winds are typically easterly. That is, they come from the east and blow to the west. Winds are always named for the direction of their origin, not the direction of their travel. All right, so an easterly wind is coming from the east. Okay, so the reason we have this going on is the combination of two things. Okay, first off, convection. So you can see here, okay, right in this area, there's a pattern of hot air rising and air moving from above in to replace it. So as hot air rises, air from further north moves in to replace it. That hot air then can't fall back down, so it's forced to travel north. This is a convection current. Okay, it's a cyclical pattern. Okay, that just moves and continually kind of cycles through. All right, when this air gets to here, it interacts with air that's circulating at higher latitudes and transfers energy to it. And you typically get warmer air moving from south to north near the surface. You also have cooler air moving from the south to the north at higher altitudes, right? So we don't get as much of a cycling pattern at our latitude, okay? But what we feel is air moving from south to north. Okay? Here near the equator, they feel air moving at the surface from north to south. Everybody follow there? All right. The problem with this is we don't feel winds moving from south to north. We feel them moving from the southwest. And here they feel them moving from the northeast. That's because as this happens, the Earth spins underneath its atmosphere. Okay? The atmosphere and the Earth are not physically connected to each other. So the Earth can kind of spin under the atmosphere a little bit. They generally move together, but the Earth's physical solid part moves a little quicker and can move underneath the atmosphere because the atmosphere is fluid. Right? It would be like if you put like a ball or something in a glass of water. You could make it spin, but the water around it would also spin, but not as fast. Okay? That's kind of what's happening with the Earth under its atmosphere. So there's this deflection, or a perceived deflection. We stand here and we feel wind doing this simply because we're moving into the air as it tries to move from north to south. So we move into it. It's kind of like if you stick your head out the window, okay, of a moving car. You don't do that. But if you did, okay, it would feel like it was windy, even if it's not. Okay, if it's not a windy day, and you just have your head out the window in the parking lot, you don't feel anything. But if you start moving, it feels suddenly like it's windy. Not because it is, but because you're moving through the air, and the air is stationary. Well, that's what gives us this perception that the winds are coming from the northeast, even though they're not. We're just moving through them as they try to go this way. All right, everybody follow on that? We call that the Coriolis effect. We'll talk about that in a minute. All right, it happens anywhere you have a spinning object underneath an atmosphere. Okay, and so we get these different bands of prevailing winds. Near the poles, okay, the cycle is always easterly again. Right, so we have easterlies near the equator, westerlies at the mid-latitudes where we live, okay, and then polar easterlies up here. Now, we're kind of right here where I drew this black line. We're right at the upper edge of the westerlies. Does the wind always come from the southwest here? No. If it comes from the north, though, we know what we're in for, don't we? Okay, winds from the northeast basically never bring good weather. Right? They're always going to bring cold air from up here, because what else can they bring? That's all they have. It's never warmer up here than it is here. Right? So it brings in cooler air from the north. So if we get a north wind, we know there's something big happening there, and there's going to be an interaction between those two different kinds of air masses that are moving, and that's usually going to result in unstable weather. All right, in the wintertime, it's probably going to mean colder temperatures and possibly blizzard conditions. In the summertime, it could mean a thunderstorm cycle where for a few days we have, it's hot, and then we get a thunderstorm later in the day. Here, question? Usually by the time they're interacting, most of that's gone. But you're right. I mean, otherwise there would always be this kind of butting of heads at that position. It's not so much a definite border like between two countries. It's more of a slight interaction, which is why around Red Deer and Edmonton, it's not as windy there as it is here or in Lethbridge. Right? Lethbridge is Canada's windy city. Okay, it's always windy there. It's always from the same direction. The trees grow bent, okay, in the direction that the wind blows. All right, but up in that area, it's much calmer because they're at the point where these are both fading out and kind of blending to each other. Yeah, that's a good question though. Okay, so near the pole, the cycling goes kind of like this. Warm air kind of is aloft because it's a little hotter. Cool air is trying to get out of its way or being pushed out of its way and trying to move south. Okay, and so you usually get polar easterlies the further north you go, and they kind of cycle around the pole. In fact, it creates like a helix or a helical pattern near the poles at on most planets. In fact, on Saturn, it looks like a hexagon. This polar vortex, okay, looks like a hexagon. And you've probably maybe heard that term before. The polar vortex is coming, and so it's going to get really, really cold sometimes in the winter. Okay, essentially what they mean is this vortex is always here, but it's getting bigger. Okay, and it's going to get big enough that it's going to expand down further than its normal range and going to cause, freezing temperatures down in areas that typically don't experience that. Okay, so if you ever hear the term polar vortex on the weather, you know you're in for something bad for the foreseeable future, okay, as that expands outwards. All right, so this is showing us how convection causes prevailing winds, okay? This process, convection, along with the spinning of the Earth, the Coriolis effect, work together to make us feel like winds are deflecting, even though they're actually just moving from north to south, okay? All right, so similar diagram, just kind of without the detail in there. Okay, you see these things here. These are called Hadley cells. They're really just a convection current. There's 3 of them on Earth. Okay, Earth is only big enough to essentially hold 3. Okay, the bigger a planet gets, the more layers of these Hadley cells you could have. I'm going to show you a video clip here that has Jupiter in it in a minute. Jupiter has like 4 or 6 bands from the equator to the pole because it's so much bigger. And it spins a lot faster. Okay? Spinning faster is going to produce more of this Coriolis effect and deflection. It actually looks in some of the videos like one part of Jupiter is going this way and the other part is going this way because Jupiter's atmosphere is opaque. You can see it better. Okay, we'll finish that up tomorrow.